And I'd like to consider at first qualitatively different types of motion that might follow from these equations of motion. Let's look at a few examples. Let's take the different examples for the potential. The first example might be a harmonic potential, meaning that the potential energy as a function of distance goes like the distance squared. That would be a harmonic potential. Think of two bodies connected by an elastic spring, and that would describe the potential energy of the two bodies connected by an elastic spring. In that case, what would the effective potential look like? The effective potential is the true potential, U of rho, plus this, in quotation marks, centrifugal force term, which goes like 1 over distance squared. For small distances, this additional term dominates. This 1 over rho squared term dominates the effective potential. And therefore we'll have a behavior like that. For large distances, 1 over rho squared becomes small, and the true potential, so the rho squared of the harmonic potential, dominates. So for large rho, it looks like that. Yeah, so here, for large rho, it behaves like rho squared, and for small rho, it behaves like 1 over rho squared. And then we have a behavior somewhere in between, where you see the shape of the effective potential. Now when we are given the total energy E, then you recognize from the shape of the effective potential that the motion of the system will always be bounded. There are two turning points at some minimum and some maximum distance, and in between these two turning points there will be a bounded periodic motion. I should note that this centrifugal term in the effective potential, it's not only proportional to 1 over rho squared, but it's also proportional to the angular momentum. And hence this extra term is present only if the angular momentum is different from 0. So you have that qualitative behavior only if the angular momentum is different from 0. So this is the case that we considered here. This is the harmonic case. Let's look next at the Kepler problem. Well, the Kepler problem comes originally from the gravitational force, where the potential energy as a function of distance goes like minus 1 over the distance. But it's not only gravity, but it's also, for example, the Coulomb potential between two electric charges also has this form. Yeah, so it's minus 1 over distance, proportional. The constant of proportionality can also be negative. If you have two equal charges, then they repel each other, and then you have an opposite sign here. All right, similar logic you draw the effective potential as a function of rho. Again, for the case that the conserved angular momentum is different from zero. Again, for small distances, this centrifugal term will dominate. So again, you have this behavior here. 1 over rho squared for L different from 0. For large distances, the true potential, the Kepler potential, dominates, which goes like minus 1 over rho. So it approaches the rho axis from below. And then in between, you have some behavior that interpolates between these two ends. It looks something like that. And here you see that already qualitatively, that the situation is a bit more complicated than in the harmonic case. In the harmonic case, we saw that you always have bounded periodic motion. In the Kepler case, you have to distinguish two different scenarios. One scenario is where you have a total energy, let me call that E1, which is smaller than 0. E1 is smaller than 0. In that case, the motion is bounded between two turning points. Again, you have rho min and rho max, and in between you have bounded periodic motion. But then you might have a second scenario where the total conserved energy is larger than 0. So you have the value somewhere here, E2, where E2 is larger than 0. If that is the case, then you still have a minimum distance. You never go below a minimum distance. It's that point here. But you don't have a maximal distance. So what happens here qualitatively is that you come from infinity, you go to that, you reach that minimal distance, you turn around, and you go back to infinity. So you have a motion from and to infinity, and that is an example of a scattering process. So in the Kepler case, you have, depending on the total energy, you have two different types of motion. Either it's bounded, that's what you see when planets moving around the sun, that's a bounded periodic motion. But you can also have some other body entering the solar system, being deflected by the gravitational field of the sun, and then exiting the solar system again. So this is not a bounded motion, but it's an example of a scattering process. Comes from infinity and goes back to infinity. And then as a final example, let us consider a potential of the type minus 1 over distance cubed. Now this is not a type of potential that you encounter in one of the fundamental forces in nature, but you can have effective forces, effective macroscopic forces that have that shape. so minus 1 over rho cubed. In that case, at small distances, the minus 1 over rho cubed, so the true potential, dominates over the 1 over rho squared of the centrifugal term. So we have here, we have the minus 1 over rho cubed dominating at small distances, and then at large distances it's the centrifugal term that dominates. It's the 1 over rho squared, so that goes to 0 like that, say, and then we interpolate between the two ends, so it looks approximately like that. And here again we have different types of motion. Let us first consider an energy here, say E1. And then we have this hump in between. So the type of motion that we will see actually will also depend not just on the energy, but also on the initial condition of the system. If the system is initially in this region here, then we will see a bounded periodic motion. Yeah, so if initially the distance is very small, then we will see that bounded periodic motion. If, on the other hand, the distance initially is large, so we are on the right side of that hump, then we will see scattering. Yeah? So then we will see body coming from infinity, turning around, going back to infinity. So then we will see scattering. And then there's yet another scenario where we have a total energy, E2, which is larger, it's higher than the peak of that hump. And then we have neither bounded periodic motion nor scattering, but we'll see a particle, the body coming from infinity, reaching the center, reaching rho equal to 0, and then going away from the center again. So actually it will pass through the center of the potential. So while in a normal scattering process, the body will approach the center of the potential only up to some minimal distance, finite minimal distance, in this case, the body will actually pass through the center of the potential. It might be deflected, so it's not a straight line, it might be deflected by some angle, but it's actually going through the center of the potential. And again here, for all these cases, it's for angular momentums different from 0. So depending on the potential that we can have qualitatively these different types of motion. And for the next, I guess for the remainder of today, we will focus on the bounded case. So we'll focus on those cases where we have bounded periodic motion. So let's focus on the situation where the effective potential has a minimum somewhere, and the total energy E is such that motion is bounded between a minimal and a maximal distance. When we start at the maximal distance, then we approach the center and we reach the point which I call B, the point of minimal distance, and we go back to maximal distance c. So let's look at sort of going once back and forth between the maximal and the minimal distance. This is the one-dimensional picture where we only have the radial coordinate rho. Let's now go back to the two-dimensional picture where we have motion in this two-dimensional plane, and rho is just one of the two cylindrical coordinates. We have, in addition, we have the angular coordinate phi. So in this two-dimensional plane, let's draw the center of the potential. Around the center of the potential, let me indicate by this circle the minimal distance that the body can reach. And then let me indicate with a larger circle the maximal distance that the body can reach. Now let's say that the body is initially here. That's our point A, and we said the point A, the starting point, is a point at maximal distance. So it's somewhere on this outer circle. Then, according to the picture on the left, the body approaches the center of the potential. We have a non-zero angular momentum, so there's going to be some motion around the center of the potential. Until eventually the body reaches a point on the inner circle. So it reaches the minimal distance to the center of the potential. This is our point B. And then the body returns to maximal distance, so to a point on the outer circle. But it doesn't have to be the same point A. The point where it touches the outer circle again, that is our point C, and that can be displaced with respect to A. And it's displaced by an angle which I call delta phi. This angle is only specified, of course, modulo multiples of 2 pi. And this motion will continue. So the body will go back to the inner circle, touch it somewhere, go back to the outer circle, and so on. And the points where the body touches the outer circle, they will keep moving, and with each sort of period, that point will move by some angle delta phi. And our next goal will be to determine that angle delta phi, because this will help us understand physically the shape of our trajectories. Let's first look at a differential equation. Let's look at how the angular coordinate phi changes as the radial coordinate changes. So the derivative of d phi with respect to rho. With the chain rule, we can write that as d phi over dt times dt over d rho. Well, the first factor, that's phi dot. The second factor, that's 1 over rho dot. We can use the area law to express phi dot as L over mu rho squared. and then we still have 1 over rho dot. For the rho dot, we use the conservation of energy, and we can write that as L over square root of 2 times reduced mass, and then we have 1 over rho squared, and the rho dot was up to a factor which I have taken in front. That was the square root of E minus the effective potential as a function of rho. At this point we have to pay attention to the sign, because for the square root we can have either the positive or the negative sign. From a sort of energy conservation gives us rho dot only up to a sign, plus or minus the square root. So we should think carefully which sign we have to pick. When we go from A to B, then in the picture top left, we go from right to left, so the rho decreases in time. So rho dot is negative. So when going from A to B, rho dot is negative, and therefore we have to use a negative sign. If on the other hand we go from B to C, then rho increases in time, and we have a positive sign. With the help of this differential equation, we can now write an expression for the delta phi. We go from A to B. We have d phi over d rho going from A to B. Going from A to B means we go from the maximal distance from the center to the minimal distance from the center. We integrate over d rho. We take the integral of d phi over d rho. This is the first half of our motion. And then we go back to the outer circle, so that's the part from B to C. So we have to add to that the contribution where we go back from the inner circle to the outer circle. We integrate over d rho, then d phi over d rho, going from B to C. The reason I wrote explicitly next to the d phi over d rho, I wrote explicitly first A to B and then B to C. That's because of the sign that we have in d phi over d rho. Because for the first part going from A to B, remember we had to use the negative sign. And for the second part going from B to C, we had to use the positive sign. So d phi over d rho going from A to B is actually minus d phi over d rho going from B to C. We can use the minus sign to change the limits of our definite integral. So then for the first integral we actually get again also an integral from rho min to rho max, and we get d phi over d rho, but then from B to C, which is the same as the second integral. So in total we have 2 times the integral from rho min to rho max, d rho, d phi over d rho, and then we apply the sign that belongs to the section from B to C. We can insert the expression that we found for d phi over d rho. together with the prefactor 2, this gives square root of 2 over mu times L, the conserved angular momentum, then the integral rho min to rho max d rho, and then we have 1 over rho squared square root of E minus the effective potential, which is a function of rho. So here you have an explicit formula for this precession angle delta phi, modulo multiples of 2 pi. The integral on the right-hand side cannot be calculated for arbitrary potentials, but for some special cases you can evaluate that integral. I would like to give you here a mathematical result without proof, which is known as Bertrand's theorem. And Bertrand's theorem says that there are only exactly two types of potential which give a closed orbit, in the sense that when you go around the center of the potential, you go around once, you come back to the original point. And that is guaranteed if the delta phi is a multiple of pi, not of 2 pi, but of pi. I'll show you that in a minute. So if delta phi is n times pi, where n is a natural number. The first type of potential that gives a closed orbit is the harmonic potential. So the potential is proportional to distance squared. For that potential, the motion looks as follows. We have here the center of our potential. We have the inner circle and the outer circle. If our starting point is A, then the motion will look like that. The body will touch the inner circle at point B and then go to the outer circle and touch it at point C. So the angle delta phi that the body has moved in going from A to C, the delta phi is equal to pi. And the point C is exactly on the opposite side of the center of the potential. And then you see, when the body continues, it will necessarily return after it has gone full circle around. It will return to the point A, and it will be a truly closed orbit. And the trajectories around the center of the potential are ellipses, where the center of the potential is at the center of the ellipse. The second type of potential where you have a closed orbit is the Kepler potential. Here the situation is the following. I draw again the center of the potential, the inner circle and the outer circle. The starting point is point A on the outer circle. The trajectory is such that the body will touch the inner circle exactly on the opposite side of the center of the potential. So the point B is here, and then the body touches the outer circle again at point C, which is identical to A. This implies that for the angle phi, that as the body goes from A to C, its angular coordinate phi changes by delta phi equal to 2 pi. And as we will see next time, the form of the trajectory is again an ellipse, but in contrast to the harmonic potential, the center of the potential is no longer at the center of the ellipse, but it's at one of the focal points of the ellipse.